In this video, we'll be talking about desirable properties of voting systems. There's an objective part to this idea and a subjective part. Like the Condorcet condition, these are going to be properties of voting systems as a whole. Some voting systems are going to have these properties, other ones are not. And these are properties that one can objectively check whether a voting system satisfies. The part that's subjective is whether or not you actually consider these to be desirable properties. To put this into context, let's remember that we can think of voting systems as social choice functions. Remember what this means. If we have a population of voters in an election, each voter is going to have their own preferences among the candidates. Then we think of the voting system as an algorithm or procedure or function that takes the voters' preferences and somehow produces a winner from those preferences. So it's a procedure for taking the preferences of individuals in the group and turning it into a preference for the group as a whole. Ideally, you want your system to verily choose the best reflection of the preferences of the voters. Of course, as we mentioned, this word best is inherently subjective. And as we've seen, different voting systems can produce different winners from the same set of voter preferences. So rather than focusing on what the word best means in this sentence, it's sort of better to think about the properties that each voting system does or does not have. And also to think about which properties you'd like your voting system to have. Some examples of properties you might want your system to have are that you might want to discourage strategic voting. You might want to discourage strategic candidacy. What I mean by this is that sometimes someone will decide to become a candidate, but just in order to hurt another candidate's chances of winning. And that might be something you want to avoid. And finally, you might want to have it a goal to make the voters as a whole as happy as possible. So the issue with the properties that I've listed here is that all of them are still a little bit vague or subjective. What we'd really like are properties that we can check objectively for a given voting system. So let me instead list a few of these. One such property that we've already talked about is the Condorcet condition, which essentially says that if there is a Condorcet candidate, that candidate wins. As we talked about, some voting systems satisfy the Condorcet condition and others don't. This was something we could check. The only subjective part is whether you decide that this is a property you'd like your voting system to have. Another property that we might want a voting system to have is called the majority condition. This says that if there is a candidate who has the majority of first preference votes, then that candidate should win. So again, this is a property of voting systems as a whole. Some voting systems will satisfy this condition and other ones won't. Let's look at a couple examples. So first I'll think about the plurality voting system, and it's a theorem that the plurality voting system does satisfy the majority condition. So why is this true? I should show you a proof. So what I'm trying to justify here is that in any election, if a candidate gets the majority of first place preference votes, then the plurality voting system will select that candidate as the winner. So if a candidate does get a majority of first preference votes, then they must have gotten more first preference votes than any other candidate. That is, they have a plurality of first preference votes. And so therefore, the plurality voting system would select that candidate as the winner. So this argument is meant to show that the plurality system will always satisfy the majority condition, that in any election it's going to satisfy the condition. The reason this argument works is that the word majority means that a candidate got more than half, more than 50% of the first preference votes, while the word plurality here means more than any other candidate. And if one candidate gets more than half the first preference votes, there's no way any other candidate could have gotten as many as that candidate. So for another example, let me now show that the board account voting system does not satisfy the majority condition. Remember that the majority condition says that if a candidate has the majority of first preference votes, that candidate should always win. So I'm just going to show you one example of that not happening in the board account voting system. That is, I'll show you a counterexample. So here is a hypothetical preference schedule, and I'll note that candidate A has the majority of first preference votes in this election. However, if we do a board account, and I'm not going to go through the details here, but if we do a board account, we would find that candidate A gets 43 points, candidate B gets 52 points, and candidate C gets 31 points. And so candidate B would win in a board account voting system. So the majority condition fails for this election under the board account voting system. And so we say that the board account voting system as a whole does not satisfy the majority condition because it failed in at least one example. One thing I'd like to point out here is that in order to show that a voting system does satisfy a condition, we need a proof. That is, we need to make logical arguments to show that a condition is met for all elections by a particular voting system. However, to show that a voting system does not satisfy a condition, we just need one counterexample, one example that shows that the voting system does not satisfy the condition in all circumstances. You can think of the reason for this difference as relating to the fact that these conditions say something that should be true for all possible elections. So to say that something has to be true for all possible elections, you need to make some kind of logical argument, something universal that will apply to all possible elections. However, to show that it doesn't apply all the time in every possible election, you just need to show one counterexample. Let's look at a couple more conditions that some voting systems satisfy and others don't. Another such property is called monotonicity. And this means that if a candidate wins an election, that they would still win if one of the voters changed their mind and moved that winning candidate up on their ballot. The idea is that moving a candidate up on the ballot shouldn't hurt them. The idea behind this property is that it's meant to prevent strategic voting, in that you wouldn't want someone to upvote a candidate that they want to lose. This property might seem like a no-brainer. Of course you'd want your voting system to be such that moving a candidate up on the ballot wouldn't cause them to lose. However, one of the voting systems that we've looked at so far does not satisfy this property, and I'll leave it to you to figure out which one. The last property that we'll talk about is called independence of irrelevant alternatives. I'll sometimes abbreviate this as IIA. What this property says is that if a candidate wins a particular election, that they still would have won if another candidate were eliminated. This property is meant to discourage both strategic voting and strategic candidacy. It discourages strategic voting because, as you may remember, a lot of the strategic voting ideas that we talked about earlier were based on logic that started with, well, candidate X is going to lose, so ... If independence of irrelevant alternatives holds for a voting system, then if candidate X was going to lose, then how you rank candidate X is not going to affect the outcome of the election anyway. There would be no harm in voting for an unpopular candidate that really is your first preference. This property also discourages strategic candidacy because a candidate cannot affect the outcome of the election unless they end up winning. Otherwise, they are one of these irrelevant alternatives. So anyway, independence of irrelevant alternatives may seem like a good property, one that you would want your voting system to have. And indeed, you could make that argument for any one of these 4 conditions that I've written down. And in fact, there are more properties that people have come up with that are considered desirable properties for a voting system to have. So a good question to ask now is, which properties do each of the voting systems that we've studied satisfy? We've already started to answer this question, and we've seen that some of these properties are satisfied by some voting systems, but not by others. And in fact, none of the voting systems that we've seen so far satisfy all 4 of the conditions. So then another question becomes natural. Are there voting systems out there that do satisfy all 4 of the conditions that we've listed here? Is there some other voting system that we just haven't talked about that satisfies all 4 of these desirable properties? And this was the question studied by Kenneth Arrow, which we'll talk about in the next video.